Everyone, just gonna wait a second for people to trickle in. Hope you're well. Mixing it up today, embedding myself in the content. Good morning. The downside of this method is I can't really see you all, but oh well. Make sure to make the chat nice and loud. But yeah, congrats, Fernando. I think you had a busy weekend last weekend, so good to see you back. Is everyone doing good? Hearing a lot of silence, so I'm gonna assume maybe y'all are a little waking up still. Yeah. Um, but yeah, life's been a little busy and chaotic, but that's just life sometimes. I'm excited to finish out the semester strong. Today's our last like real class day. Next week is the final, and it's been a pleasure. But we'll get sappy again later. But yeah, just wanted to call out. It's been a lot of fun. But I'm just gonna jump right into the slides, and then we'll kind of unpack further from there. But I think some general news that you all will uh, appreciate. So, agenda, reminders, we'll do the code word, we'll do the lab walkthrough, and then I'm actually unlocking the final today at 10. And so, once we go through the lab walkthrough, happy to walk through the final with you all. Um, and yeah, give you a head start. It's open essentially, it's starting 10, and then it's due by the 19th at 11:59 p.m. But let's get into it. Reminders. So we have two more classes today and next Saturday. It's kind of wild. This semester flew by like crazy, more than previous semesters, I'll have to say. So uh, it's been a pleasure, but yeah, it's been really quick too. So let's stay in touch, and next week at the final, we'll do some like contact exchanging as well, so that uh, we can join each other's professional networks. But please do make sure to attend next week, unless you've previously reached out to me and let me know, or have some extenuating circumstance or medical emergency. Please do show up. We're not going to take the full 3.5 hours, maybe like an hour tops if we're being extremely long-winded, more realistically, like half an hour to 45 minutes. So uh, just come on by next weekend, and then we'll kind of close out the semester together. But yeah, that's it on class sessions. In terms of assignments, um, Lab 5, which is from last week, is due today at 11:59 p.m. Hopefully get those in sooner, but that's the deadline. After that, it's considered late. Along those lines, I just sent an email about any kind of outstanding assignments you haven't turned in yet. Please do turn those in. Late credit is great credit. So just get those points and finish the semester strong. In terms of Lab 6 today, I've made the executive decision to make it entirely extra credit. So I strongly encourage you to complete it and turn it in, because I'm going to do it with you. And so this is an easy way to earn points, extra credit points for your grade, but it's not going to detract from your score. And so, yeah, lab 6, which is today, is an extra credit lab that's due next Saturday before 11:59. So just wanted to call that out. Um, and I've updated Canvas accordingly. The final is not extra credit, but it's open at 10 and it'll be due by the 19th at 11:59, along with the two other extra credit opportunities, one for lab 4, one for lab 5. And so those are each 5 points, but do get those in if you want to get some extra points for your final grade. And like my email said today, I'm going to do some grading this weekend. So your scores on Canvas will be updated to anything that's been turned in by this weekend. So realistically, I'll wait until Sunday, tomorrow, so that I can get any submissions for Lab 5 for tonight. And then I'm going to grade everything up through Lab 5. So that's it on assignments and class sessions. Are there any questions on either of those topics? I'll take the silence as sounds good. Or this is horrible. Please do write in chat or unmute yourself. Cool. Thank you. Yeah. That's the one problem with online teaching is not getting feedback in terms of like seeing faces like scowls or like smiles. So yeah, make sure to make that chat loud. But thank you. This feedback is helpful. So I'm glad that it is well received. The code word of the day, Washingtonia filifera. I'll I'll type it in chat. Tonia filifera. Right? Dude, so there's so yeah, Donnie for the knowledge. They're all over where I live, in 29 Palms, hence the name probably. But yeah, they're majestic, weird plants. Uh, cool. So make sure to submit this code word in Canvas before 1:30 p.m. Pacific today. I have a time gated that like window to submit the code words, so make sure to get that in so I know you were here. Um, and please don't share it with people that aren't here. I mean, like you'll do what you do, but like it encourages showing up. So I know there's ways around the system. Um, let's get to coding. And this is today, years old us doing Python stuff. We're hacker people. We're hacking into NASA with HTML. No, we're using Python actually. So let's get into it. And I'm going to now toggle out of I'm getting my OBSC legs again, how to do things, but I'm having to use my mouse, which it's terrible. I need to get like a Stream Deck or something. Uh, all right. Spectral indices with Python. So this is another 10-point lab, but it's extra credit. I'm just not mentioning that in these instructions, but on Canvas, you'll note that it is, but this is a great opportunity to bump your grade up in a good way. And so we'll do like a high level overview of what we're doing today. Need to refresh this page because there is no like optional extra credit in addition because it's already just an extra credit lab. So that's just like stale for some reason. That's fine. So we're gonna create a lab or a repo in GitHub like we've been doing. We're gonna use a template repo, and then we're gonna go through these 8 lessons from the Earth Lab at CU Boulder. Their intermediate Earth data science textbook. And so we're going to cover a variety of topics, predominantly around how fire impacts vegetation and how scientists, researchers, engineers, industry practitioners use remote sensing to monitor said changes. In the West, particularly California, especially um, kind of the coastal chaparral, oak woodland areas that aren't too far from Long Beach are very prone to fire, especially with climate doing weird things these days. And so um, it's going to be interesting to see some of the methods that are used slightly at a more zoomed in scale than maybe you're familiar with if you've done work with Dr. Laris and others in the department with the UAVs and drones, or UAS. And so we're going to be looking at how practitioners use MODIS data, Landsat data, NAIP data, and try to gain insights about the impacts of wildfire on vegetation. But similar uh, methods can be used with higher resolution data from UAS platforms. So I hope this kind of helps you also think about problems and projects occurring more locally and not just in this kind of random Colorado test site that's maybe not the most relevant to your day-to-day life. So after that, after doing these lessons or along the way, we're going to commit our changes. But once we're done, we're going to submit the URL on Canvas and then ignore the step 7. I deleted it, but maybe I forgot to save it. But there it is. Okay. Updated in real time. So there's not an additional extra credit. It's just the whole thing is extra credit. Um, do we have any questions about the overview of today's assignment? Or are we kind of good to just proceed and just hack away? I'm just checking the chat or listening in. Okay, hack away. Love it. Okay, let me toggle. Nice. Okay, so I'm gonna create a repository using this template repo. I'll share the link in chat to make your lives a little easier. So let's create a new repository. And then I'm going to call it GISC 606 Lab 6. Make sure it's public so that I can view it and give you that perfect score that you deserve. Let's create a repository. And then we're going to open it in a code space. And you can do that by clicking or smashing this green button. If we're doing things online, you can't just click it, you have to smash it. So we're going to smash this create code space on main button and then proceed with hacking. This is not a sponsored post, but shout out to the cold brew concentrate from Trader Joe's. It's very convenient and delicious. It's a great way to start your morning. I'm okay with getting sponsored, but I'm not sponsored yet. All right, so it's installing our requirements for pip and declared in the requirements.txt file. You can see namely IPy widgets, matplotlib, pandas, torch vision, tqdm. These are some like machine learning libraries that we're not going to really use, but as you dive deeper in Python, which I hope you do continue, yeah, use for 10% off at TJ Cold Brew at checkout. Um, I just need to put that little disclaimer in the video, like sponsored. I don't know what Cal State Long Beach would think of that. But yeah, thank you, Fernando. Please do. Yeah, let's make it happen. It's the collab that the universe needs in these trying times. But yeah, as you dive deeper into Python, you'll have more complex requirements.txt files that you might create yourself or inherit from others. And so just as this automated script magically installed using the pip install dash R or dash, yeah, requirements.txt. Um, you can do that and avoid kind of the manual inline pip installs that we've been doing throughout the semester. Yeah, Fernando, I think that that's your directive for the remainder of the semester. Um, all right, so we have a workspace ready. I'm going to stop talking about getting sponsored. Um, and I'm going to create a file called coldsprings.overview.ipynb. I will say if I do get sponsored, I'll make sure to send you all some Trader Joe's cold brew concentrate because you were part of making it happen. Okay. Cold Springs overview dot txt. No, it should be dot ipynb. Cold Springs overview dot ipynb. Awesome. Will I settle for better parking? Yeah, I'll take that. Priority. That would be kind of nice, actually. Just like the golden parking pass. Uh, that would be sick. Okay. Now that I don't live in like a really densely populated urban area, there's not a Trader Joe's near me, so I have to drive like 45 minutes to an hour and go to like Palm Springs. And some of them are actually not that crowded, which is nice. So coming from like LA, it's a blessing. So we have our Cold Springs overview notebook. Let's select the Python 3.10.13. Yeah, I think that if anything, we need to get the next cohort of MSGIS students to do a spatial analysis to convince the Trader Joe's corporate to put a Trader Joe's near Paca. If we can make that happen, automatic A's for everyone. Um, all right. Yeah, Fernando, let's talk. Uh, oh my God, that's so funny. I didn't even realize that. Okay, sick. Yeah, let's talk. Um, okay, so the Cold Springs fire. Let me toggle back to lab instructions. So we're going to learn about this wildfire. Yeah, do it for the aromatic A's or automatic A's. Sorry, aromatic. I'm thinking about coffee. It's aromatic. Okay. Um, so the Cold Springs wildfire happened in July 9th, 2016, or between the 9th and the 14th in 2016. So summertime, it's probably dry out there, hotter than usual. You could expect that the conditions are ripe for um, wildfire potentially. And so a total of 528 acres of land burned, which, if you think about it, is not that large. I mean, I'm sure there was damage and it's a bummer that it happened, but uh, at least in California, we hear about these thousands and thousands of acre fires, or tens of thousands of acres. And so, in the grand scheme of wildfires, 528 acres isn't super large, but it's a useful kind of study site, almost like an experiment that we can use to learn more about how scientists are able to extract information using these sensors and analytical techniques. And so this chapter will kind of uh, empower us to list the causes and impacts of the wildfire, some of which I was postulating about, but I think we'll dive deeper into the more data backed hypotheses, and then we'll explain how scientists can use field measurements and remote sensing to study wildfire impacts. So this is kind of similar to how we were studying tree measurements using like diameter at breast height measurements from on the ground or in situ versus the LiDAR data. So this is kind of taking that similar approach of kind of parallel data collection using different sensor types and applying it more to wildfires. We're going to list two primary vegetation indices that are used to study wildfire impacts, and then four primary sources of remote sensing data that can be used to study wildfire. So wildfires can occur naturally or be triggered by humans. We've heard about those unfortunate uh, baby gender reveals that triggered like fires. It's just like, yeah, or lightning. And so it's kind of random, but sometimes really disappointing initial cause of fires. Um, and researchers at the University of Colorado Earth Lab, which are the authors of this textbook, they've shown that humans are responsible for starting the vast majority of wildfires. 84% is not trivial. I'll copy a link to, or I'll share the link to this article in Science Mag from the authors from 2017. But that's kind of wild to think that our fellow humans are to blame for a lot of this. Oh no, wasn't Alex to blame for the fire? Wouldn't be surprised. We'll have to do some research on that. And so the most common causes of human-induced fires are intentional acts of arson, campfires, debris burning, discarded cigarettes, and new babies. We'll have to submit a pull request to have that here. Um, so humans also increase the prevalence of wildfire indirectly through climate change. And so these warmer and drier conditions from climate change often lead to drought. And spring is coming sooner specifically, and it makes the mountain snow melt earlier, which increases the likelihood of drought later in the summer. So if you think about July time when the Cold Springs fire happened, yeah, that's like midsummer or early midsummer. So that's even earlier than necessarily expected for like a late summer drought. Um, so wildfires can be devastating and rejuvenating for the environment. I don't know if you've taken any kind of fire ecology or biogeography courses previously, but there's some species of plants that they don't really start to bloom or open their cones until after a fire. And so fire can be this just like wonderfully transformative event for certain species that enables them to kind of uh, begin their lives as plants. Whereas for others, it's absolutely devastating. And also, you can see in this photo, it's not just the plant life that's impacted, it's also wildlife that were residing inside of these plant communities. And so it's a super devastating event to kind of the more quote unquote natural environment. But then if you think about wildfire in the US, oftentimes it's happening at these intersections, the interface of wildland and more urban or semi-urban rural communities. And so it's not just elk and squirrels and trees, it's people that are at risk for these wildfire hazards. And so let's now pivot to wildfire in the US. Many fires have extreme impacts on humans, like I was alluding to. The deadliest fire in US history was in northeastern Wisconsin in the late 1800s, and it killed 2,500 people. That's insane. And it burned over 1 million acres of land. This is why I was kind of um, maybe minimizing the 500-acre stat for the Cold Springs fire, because yeah, like 1.2 million acres. I can't even fathom how big that is. Um, yeah. And I mean, thousands of people died. That's crazy. I don't think we've had anything like this century. Maybe in like urban, densely populated, like factory or warehouse fires, but nothing kind of like a wildfire that just decimated that kind of uh, quantity of terrain. But living in the West, I think we've all kind of grown up or quickly became accustomed to, if we moved here later in life, the risk and presence of wildfires, especially in California. And I mean, this year's been a little weird with rain. weird in the good way that it's been kind of more damp than usual. But growing up in California, I can say that it's been fairly dry since the 2000s, I'd say. We had an El Nino when I was a child, and that was the last time it was dumping rain. But besides that, it's been a fairly drought-ridden decade or two. And so fires have been an increasingly common event in our kind of broader region. So kind of pivoting more uh, to the economic impacts of fire, which is a lot of the reason why there's so much research and investment into studying fires, is in recent history, 14 people were killed in the San Diego County fire in 2003, the Cedar Fire, and it destroyed 2,200 buildings and 280,000 acres of land. That's also pretty unimaginable in terms of that damage. I'm looking at the Colorado figure for the 217 million. I'm sure the one in California was that, but doubled or more, 500 million, maybe going up to a billion. Especially San Diego County is not cheap. That was a lot of residences that were, or buildings that were destroyed, and acreage of land. So um, fires can have tremendous economic impacts alongside the devastating kind of ecological and rejuvenating ecological impacts. So it's complicated, as most interesting things are. And so now that we've set some context for wildfires generally, and then zooming into the US impacts, let's talk about the Cold Springs wildfire from 2016. It's not the biggest fire, as we've kind of already talked about, but it's interesting because I think there was a lot of overlapping data that was able to be collected and used to gather insights about what happened. So this fire was first reported northeast of Netherland, Colorado, near the Golden Gate Canyon State Park. And here's a map showing the kind of area of Nederland in relation to Denver. I guess Denver is, oh, it's here. So it's kind of a mountain outskirt. I wouldn't call it suburb, but maybe like on the hinterlands of Denver. I was in Denver earlier this year, and it is surprisingly flat. This whole area is just like weirdly flat and kind of boring looking. So it must be nice up here, but I didn't get a chance to go there. And so this map shows the extent of the Cold Springs fire just outside of Nederland. And you can see that it's not the largest, but it had a pretty considerable extent in the region. And it's going over varied kind of mountainous terrain. You can see with these topological markings. And so there's also some water features, it seems, but I think over the course of today's exercises, we'll get more insight into the vegetation, how it was, and how it is after the fire. And so this is a human-started wildfire, and it was officially, whatever that means, quote unquote, officially extinguished on the 14th after 5 days. So 528 acres of land, 430 of which were on privately owned land, and 98 of which were on U.S. Forest Service property. And 8 homes were lost. So for 8 people or 8 families, that's a pretty significant impact. And here's some live footage or photography from firefighters working on the scene on the 11th, which was midway kind of through their firefighting efforts. And so the fire burned predominantly in pine forests of the lodgepole and ponderosa variety. And so I think we'll learn more about the underlying maybe subcanopy vegetation or the different types of plants that were there. But this differs tremendously from, I think, our West Coast California context, where it's a lot of shrubs and a ton of annual grasses that just senesce like crazy and become like tinder. And so I don't know if they have that same type of annual vegetation fire uh, load there underneath this pine forest, but I think we'll learn more today. And so we heard above that this fire was caused by humans, but it's actually been attributed to a campfire that was not properly extinguished during a countywide fire ban. So two transient men from Alabama were charged with fourth-degree arson. That's kind of wild. And they were sentenced with 2 years of work release, followed by 4 years of probation. And they must pay restitution up to $1.25 million. So these guys definitely screwed up. Um, that's a bummer for everyone involved. But there's a reason why there's campfire bans in a lot of places, and why using like a propane stove, propane like fireplace, fire pit kind of thing is strongly recommended because stuff like this can happen. So this is 2 months after the Cold Springs wildfire, and you can see that the area is still pretty devastated. Nothing is really growing in this understory yet. I guess 2 months after July is September. So yeah, maybe in the following spring we'll see some growth, but any animals that were kind of using this as grazing land or a place to live and hide from predators are kind of forced to migrate elsewhere and then compete with whatever animals were there in the surrounding areas already. And so there were significant impacts in the surrounding areas as well. 2,000 people were forced to evacuate the town of Netherland because of the fire risk. And you can see some of the property damage that occurred here. Someone lost a few nice classic cars, which is a bummer. Um, but yeah, I'm guessing this is a fairly wealthy area, to be honest. So I'm sure these people are going to be financially fine. So I wouldn't lose sleep over it, especially if they came out with their lives. But it's still a huge bummer and was preventable. So as you can see, we didn't actually have any content for this lesson. So let's just do a print statement and say wildfires are scary, man. And so let's save that, commit that to our repo, and then we'll commit on or continue on with the remaining lessons. Okay, cool. I'm gonna create a new notebook. I'm gonna toggle back to GitHub real quick. But you can see I just committed everything. Everything's up to date. So I'm gonna create a new notebook called Field Methods, and then we're gonna jump into lesson 2 for today. And then we'll select the Python 3.10.13 kernel as usual. And then I'm going to return now to the lesson. So fires naturally occur in most ecological systems, but they still have large impacts on humans and wildlife. And so there's a significant effort to study fire in order to, among other things, predict future fire behavior and potentially save lives and minimize evacuation efforts, understand how humans impact fire intensity and frequency over time, and understand how fire is impacted by climate. So the impacts of wildfires, like the Cold Springs fire, can be measured in a number of ways, including field surveys or remote sensing. And so field surveys involve humans taking manual measurements of vegetation loss and soil characteristics at a fire site. So these tend to happen after the event. because you can't really predict where a wildfire is going to occur. And so these field surveys are often postmortems of the event. In contrast, remote sensing involves getting data collected from satellites, unmanned aerial vehicles, and planes to calculate quantitative metrics. This can include burn severity, changes before versus after the burn in vegetation, and differences between the burn site and areas around it that did not burn. This data can also be used to monitor ecosystem recovery. And so this remote sensing data, depending on the platform, is being continuously collected over all study sites around the world. And so when a fire happens, you can just go back a day or whenever the last data was collected for a particular sensor platform and get information about your study site, and then again return for the following data collected of your burned area from that same platform. Things can happen like cloudy days, which are a problem with satellite data, but when you're using drones and aerial platforms like planes, that's less or a different kind of issue. And so using field surveys and remote sensing together are a nicely complementary pair to better understand changes and maybe why things happen to begin with, or why they unfolded differently. So we're going to learn more about how scientists use field surveys to study the impacts of wildfire in this lesson. So I imagine there's not going to be a ton of Python code in this lesson, so I apologize in advance, but it's one of those context lessons that are helpful. So when studying fire in the field, scientists will often collect vegetation and soil samples either before and after or in burned and unburned areas. So even within a place that is burned, not everything is necessarily burned. So you can kind of gather a sample kind of at the boundary line of where things have burned and where things have not burned. And so these scientists calculate standing biomass and measure soil properties to better understand the characteristics of the landscape. And so standing biomass is the total mass of living matter in a particular area, including trees, shrubs, and grasses. So across living matter of the plant type, fire can be devastating and just indiscriminately reduce standing biomass. And it can be standing biomass can be broken down by type or species, such as shrub biomass, woody plant biomass, or biomass of grasses. And so the biomass of grasses and woody plants correlates to increased wildfire risk, as these are species that most commonly fuel fires. So the way that scientists calculate standing biomass of a tree is to measure the tree's diameter and sometimes the height, and then use an equation based on previous studies of the tree species to calculate biomass. So foresters, arborists, plant ecologists have over time created these kind of formulas and kind of lookup tables to estimate the biomass of a tree depending on certain key measurements, whether they be the diameter, the height, or I mean, I think that's basically it. So this photo shows a postdoc and some grad students doing some field surveys, measuring the diameter of the tree at the, I guess, base. The most common metric I've heard is diameter at breast height. So it's kind of like at your chest level. This is, I guess, diameter at foot height, or maybe diameter at root level. And here they're calculating standing biomass at the Cold Springs fire site in November of the year that it occurred. So what is that, 4 months after the event? And here they're showing more field work occurring in November of that year. You can see that it's transitioned from summer into, I guess, fall. It's not technically winter there yet, but there's plenty of snow. So in addition to diameter measurements of trees, soil measurements, including content of organic material and nutrients like nitrogen, phosphorus and sulfur are useful for researchers. They can help with assessing fire severity. For example, a more intense fire can burn the entire organic layer on the surface of the soil. So scientists can kind of measure the organic content of these burned areas as a proxy to kind of determine how intense a fire was. Um, so they might also measure physical properties such as pore space and water repellency of the soil, and particularly water repellency caused by a fire may increase erosion and remove soil from the fire site. So there's not only primary effects of these wildfire, namely like burning a bunch of plants, potentially killing things. There's secondary impacts like erosion, maybe some landslides, depending on where it's occurring in the terrain. So wildfires, it can be pretty devastating. And then finally, field surveys are often performed to categorize the vegetation health a little more categorically, or yeah, categorizing it categorically, more qualitatively, let's say. And so they'll measure things like percentage of leaves alive. I guess that's quantitative, but it's kind of, yeah, it's a little more hand wavy. Or count the number of pine cones in a given area to see if seeds survived. Okay, that's quantitative measures. My bad. But you can see there's a lot of different ways that these researchers are counting things in the landscape to understand what happened, how severe it was, and maybe why it happened in certain places versus others. So, like I mentioned, this is another kind of no Python lesson. So let's say print yield surveys sound valuable, but like a lot of work. I can say that from personal experience. That's one of the reasons that I was kind of drawn to remote sensing and programming more specifically, is that you're kind of decoupled from having to be anywhere. Like it's cool going to study places and stuff, but like I like being home. Um, it's nice to not have to be somewhere. So I like remote sensing methods because if you're doing drone stuff, you kind of have to be there. But if you're using satellites or planes, you can just download data and do your analysis wherever you are. Um, Same with code. So let's commit this change to our repository and continue on with lesson 3. Okay. I'm going to create a file called remote sensing. So aptly named. Let's open it up and select the Python 3.10.13 kernel. And then I'm going to return to the lab instructions and we'll march onward. So we're going to explain how scientists use remote sensing to study wildfire impacts, lists 2 primary indices that are used to study wildfire impacts, and then 4 primary sources of remote sensing data that can be used to study wildfire impacts. Part of me thinks this is another no-code lesson, so let me aggressively scroll through this whole thing, and then we'll all ruin it. Oh, yeah, okay. Well, I'm going to talk at you for a little longer, so buckle in. Let's go. So, using remote sensing data to understand fire impacts. Remote sensing data are often used to study fires. Yeah. Remote sensing data collected from satellites and airplanes allow you to gather information about the landscape over time. Data collected from satellites like Landsat and MODIS are freely available and collected regularly across the globe. Since remote sensing data are collected over time, they can be used to, among other things, track changes in vegetation, understand the areas and intensity of fires, monitor the post-fire vegetation dynamics of burned areas. Like I've said previously, in the semester, this whole course is kind of heavily focused on more natural, environmental, non-developed areas, and the application of remote sensing to study those. If you're more of like an urban GIS person, I'm sorry. There's a ton of remote sensing stuff for that. We're just not really covering it this semester. But if you're interested in that, do reach out to me and I have resources to share. Perhaps in future iterations of this class, I'll be better about scattering a variety of topics, but apologies. So vegetation indices can be useful tools for quantifying and visualizing the before and after effects of wildfire. These indices are calculations performed on specific spectral bands of remotely sensed imagery to accentuate a particular vegetation characteristic. They can be used for anything from understanding disasters like floods or fires to deciding when to irrigate crops. So this week, we're really building on last week where we were learning about multispectral imagery and how there's specific kind of like bands of data. This week, we're taking those bands of data and kind of doing special recipe secret sauce math on them to accentuate features that matter to us as an investigator. So the first such vegetation index that we're going to talk about is Normalized Difference Vegetation Index, or NDVI. You might have heard of this in previous courses or just in your literature reviews for your, I guess, other courses or your thesis project. But NDVI, it's an index used to measure the greenness of an area. So the purpose of studying wildfires like the Cold Springs fire, NDVI lets us visualize and quantify vegetation health before and after the fire. I will say that NDVI is a more like basic metric of vegetation health. There's more like cutting edge, fancier algorithms used to measure that, but as like at a landscape scale, it's often hard to beat NDVI because of just the availability of the spectral bands across a variety of sensors. And so it's just a super nice index to study plants. So you can also use NDVI to track the rate of vegetation growing back in a burned area. So like I said, NDVI is collected by a lot of platforms, and particularly platforms that are flying over areas fairly continuously. And so you can create like a time series of NDVI data to track how fast a landscape is greening up, just generally in response to like environmental conditions like the natural rain, sunshine, et cetera, but then also these kind of events like wildfire or like an earthquake or whatever. And so these time series of vegetation indicators are super helpful to understand what's going on in an ecosystem, particularly to track speed of recovery. And so in this course, or in this like today, essentially, we're going to use Python to calculate NDVI and create images like this one right here. So showing the NDVI in June 2003 of the British Isles and parts of Europe. And to understand this scale of data, we have darker green indicates the most lush vegetation, so here, whereas red areas lack any vegetation. Here's another example of an NDVI image of agricultural fields using center pivot irrigation. Red areas signify healthier vegetation, whereas blue areas do not. So another index that we're going to use today, and you might encounter in your studies and applied practices, is the normalized burn ratio, or NBR. And it's another vegetation index that's used to visualize, it's used to visualize burned areas and understand fire severity. And so you can perform a calculation on remotely sensed images taken prior to a fire and then after, and then calculate the difference between the two to kind of understand the delta for the change. And so this difference NBR image is what is used to kind of display that change. And so this is an example of a difference NVR image for the Cold Springs fire. And we're going to create one of these today. And so I think it's increase the areas where it got greener are in green, where the areas that it kind of became less green are in this like peachy, pinkish, white sort of color. Additionally, here's a more zoomed out view from Landsat, and you can see the areas that are most impacted by the fire are in this lightest color, which kind of equate with that outline that we've been seeing so far today of the fire boundary. And again, here's another way to visualize that using the remotely sensed imagery to show the difference in NBR. And so we're going to create a lot of this today. And finishing out this little lesson, it's a reminder of where to find these kind of useful data. Ones that'll be most easily, freely available to you for this purpose are NAIP, Landsat, and MODIS, each of which have different spatial and temporal resolutions listed on the page. I'm not going to go through these tech specs, but I encourage you to check them out. There's a variety of other providers, namely for-profit businesses that are collecting high resolution data across the globe. So there's alternatives, but they involve payment. It's not for free. Whereas these MODIS Landsat data, it is for free, which is nice. So let's, what are we going to call this? Okay, I'm going to toggle back to code spaces. We'll just do another print statement. Remote sensing, ooh, spelling, to study wildfire. Cool. So let's commit that and continue on. Finish lesson 3. Let it sync. Okay, come on, dude. There we go. Okay. Strange. So let's close this one. And then I'm going to create a notebook called MODIS. So touch modis.ipynb. And then we'll open it and select our trusty Python 3.10.13 kernel. And then I'm going to toggle to the instructions. So we're going to list some MODIS spectral bands and identify which bands should be used to calculate normalized burn ratio. Then we're actually going to get into Python and import and stack MODIS imagery, and then scale MODIS surface reflectance values to the appropriate ranges. It's all with Python and all with provided data, so you don't have to worry about downloading it from MODIS or registering for any of that you would in your actual like applied practice of this. So let's get going. So intro to MODIS imagery. It's the moderate resolution imaging spectrometer, MODIS. That's a satellite-based instrument that continuously collects data over the Earth's surface. Currently, MODIS has the finest temporal resolution of the publicly available remote sensing data, spanning the entire globe every 24 hours. MODIS collects data across 36 spectral bands. However, in this class, we're only going to work with the first 7. So you can already see like there's a ton of data, like daily data, 36 bands. It's a lot. So, but we'll see quickly that it's not super, super high resolution. And here you can see it's 250 or 500 meter by 500 meter pixels. So those are pretty massive compared to like UAS data that's on the scale of centimeters or inches. So the Modis surface reflectance product, or the MOD 09GA. There are many different Modis data products. They're data sets that are processed for use in science. And so in this class, we're going to be using the MOD 09GA product, which is a reflectance product that includes the first 7 bands of Modis. The normal range of surface reflectances is 0 to 1, where 1 is the brightest value and 0 is the darkest value. Surface reflectance is a measure of the spectral reflectance of the Earth's surface as it would be measured if on the ground. So you can think of it as what your eye would see, except of course, your eye cannot see light outside of the visible part of the electromagnetic spectrum. So Modis provides many standardized products, including the one we're going to use today. The product we're using today provides surface reflectance at a spatial resolution of 500 meters across the 7 spectral bands listed in the table above. So according to the Land Surface Reflectance Science Computing Facility, who creates this Modis product, the products are estimates of the surface spectral reflectance for each band as it would be measured at ground level, as if there were no atmospheric scattering or absorption. It corrects for the effects of atmospheric gases, aerosols, and thin cirrus clouds. So additionally, there's some band metadata for this product. We've kind of encountered metadata previously in this course, but this is a slightly more involved table showing just units, the data type, how it's stored on the computer, the no data value, the valid range, and a scaling factor that's used to compress the data. So I encourage you to think about these questions in your head, but we're going to continue on. So let's identify Modis bands for NBR calculations. So this week in class, we're going to be calculating NBR with the Modis data. Even though we can calculate the same vegetation indices with many different remote sensing products, a bunch of typos in that sentence, we're going to remember the bands for each remote sensing data are different. And so let's review the table above to understand the band ranges for the Modis sensor. And recall that the NBR index will work with any multispectral sensor with an NIR band between 760 and 900 nanometers and a shortwave infrared band between 2800 and 2350 nanometers. So let's scroll up here. So this one should work here, the shortwave reflectance, and then I already forgot the other range numbers, 760 to 900. I guess this one. Okay. Let's pivot to some Python and actually get to coding. So I'm going to toggle away from the instructions and we're going to install some things that we haven't installed yet with pip, and then we'll import some stuff. But first I need to sponsor post, drink some cold brew concentrate. Message from our sponsors. True Earth. No, I watch too much YouTube. So we're gonna need GeoPandas. We're gonna need Rio X-ray, X-ray, Raster.io, EarthPy. I think Shapely gets installed with GeoPandas, but I'll just do it anyway. So you can see it's just downloading a bunch of stuff for us, which is nice. Once that's complete, we're gonna import the required libraries for today and actually get to hacking. So glob, import glob, import OS. as NP, import numpy.ma as MA, import matplotlib.pyplot as PLT, import geopandas as GPV, import Rio X-array as RXR, import X-array as XR from raster.io.plot, import plotting extent, import earth as ET, import, my goodness, that's by spatial as ES, import earth.plot as EP, from shapely.geometry, import box. Oof, that was a lot. Need to collect myself after that. Okay. Data equals. What was the last pip install? I'll share it with you. Share it in chat. So data equals ET get, or ET data get data cold spring fire. And then let's set our working directory to OS. That's join ETIO home earth analytics data. We got an error. What line? Where did I mess up? Oh, it's supposed to be Cold Springs fire. It's fine. Typos happen. It's no biggie. So it's downloading data, and then it's going to set our working directory. So we're going to use glob again to create a list of modis surface reflectance rasters using the keyword and extension surreflb and the wildcard **tiff. And so once this is complete downloading, I'll start typing in the next cell to do this glob. Goodness. It's probably a fairly large data set, and then all of us are downloading it at once, and so we're getting rate limited. But that's all good. Damn. Guess we just got to hang out and wait together. Is anyone else, is it taking them this long to download the data? Take that as a no. I'm not seeing anything in chat. Yeah. It's taking a second. Is this happening to anyone else? Just write in chat or unmute. Yeah. Probably gonna stop it and then run them as separate lines, just because they kind of not into that. Let's try again. We'll just take another 10 minutes. Okay, that was way faster. Okay, I don't know what was going on. I think my computer was just like freaking out. Um, Glad that's fixed. Now let's do the glob stuff that I was talking about previously. Cool. So we'll do modus fans pre-list equals glob os path join. And then we want to do cold springs fire modus reflectance 07 July 2016 crop and then underscore sir underscore refl underscore b asterisk dot tiff. Okay. So let's just output this. So it's an empty list. Love that. That's odd. Let's see what's inside that file, because it might just be a typo. ls cold springs fire modus reflectance not access modus reflectance. Saying no such file or directory. Struggling today. Okay. That's why. But interesting. Cannot access that. Okay. So cold string fire slash modus slash reflectance. Okay. 07 July 2016 slash crop. Okay. So there are files in there. Something was just not working as expected. Oh, there needs to be a asterisk. I don't think I put that there. That's why. Okay. There we go. So it was a typo on my part. I was missing an asterisk here, and so it just wasn't it wasn't picking up anything in that folder. It happens. So now let's sort that list and return it. Modus main. And so now it's sorted by band number, which is nice. Here it was not. Now let's create a function, kind of a convenience function to combine a list of TIFFs in the same coordinate reference system and of the same extent into an X-array object. And it takes a list of TIFF file paths as input, and it's going to return an X-array object with all the TIFFs in the list merged into a single X-array data array object. So let's create a function called combine TIFFs, and it takes TIFF list as input So we can learn a little bit about Python doc strings really quickly. These are just like nice ways to like generate docs for you when you do help on your function. So I'll show what I mean by that in a second. A function that spelling that combines whatever. It's good enough. A list of TIFFs in the same CRS and of the same extent into an X array object. And so we'll do parameters. Diff list. List of paths to the TIFF files that you wish to combine. And so this is all optional, creating this internal documentation. But if someone else is using your script or function, it's super helpful if there's some explanation. Zip files in the list merge into a single object. Okay, awesome. So we have our doc string. Now we can do our actual function logic. Out XR, empty list. For I, TIFF path in enumerate TIFF list. Out XR dot append. RXR, open, raster IO, TIFF path, masked equals true, dot squeeze. So this assumes that you have Rio X-array installed for this function to work. XR I and equals I plus 1. And then we want to return XR concat out XR on the band dimension so that we have a single X-array object concatenated from this list that we have. So now we have this function. If I do help combine TIFFs, it outputs all of the text that we created in our doc string so that if someone wants to learn about our function, they can really easily do it from the Jupyter Notebook. So let's use that function to create a new Rio X-array object from the list of bands that we created with glob. And so then we'll be able to import the modus bands and create an RGB plot. So let's do that like this. Modus bands pre equals combine TIFFs modus bands pre-list. And then modus bands pre. Let's just output it and see what we get. Nice. So it's an X array, data array, 7 bands, 2400 by 2400. Spatial reference information. This is great. But you'll notice that the data is not scaled 0 to 1. It's in thousands. That's something we'll handle later, but just something to note. So let's actually plot our modus data that we have here, specifically the red, green, and blue bands. So let's use EarthPy plotting and the plot RGB method to plot an RGB image. So we'll do modus bands pre, specifically the values, which is kind of shorthand for the NumPy array of information. And then we'll specify which bands to pass into the RGB layers for rendering. So we'll do 0, 3, and 2. And then we'll specify a title, surface, reflectance, modus, RGB bands. And then we'll use our trusty old friend pyplot and do show. And you'll see that I have a typo. Plot, it's not plot RBG, it's plot RGB. It happens. It's thinking, it thought. And now we have this lovely, albeit a bit muted, RGB image of surface reflectance for the study area. And you can see there's some cloud cover, but I think that we'll do some enhancements on this data to make it a little more interesting for us. So let's explore the data values that we've gotten. To begin, we'll identify the minimum and maximum values of the first band, the red band. So let's do print modus bands pre 1 min modus bands pre 1 max. So we'll note that the min -100, the max 10,039. So let's actually go a step further. Let's crop the data for our assignment or for this lesson. And we can do that in 2 easy steps. We'll reproject the fire boundary so it's in the same CRS as our modus data, and then crop the modus data using Rio clip. So let's get into that. We're going to need to open the fire boundary and then do a few operations. So, because this is the whole area that we're not interested in, we need to clip it just to the study site that we want to focus on today. So let's open the fire boundary. OS path join Springs fire vector layers fire boundary geomac CO cold Springs 2016 typo already 2016 0711 2200 BD83.shp. Okay, now let's use GeoPandas to read that into a geodata frame. Equals GPD read file fire boundary path fire bound sin. So we want to just get the coordinate reference system reprojected, or we want to get the fire boundary reprojected to the modus coordinate reference system. So firebound sin equals fire boundary to CRS modus bands pre.rio.crs. So here you notice I have a typo. Just need to add a U, and we're good. And then let's use the shapely box method or shapely geometry box method to create a boundary box from our fiery boundaries or fire boundaries. So our fire boundaries are this weird kind of squiggly polygon thingy. We want to just get the square boundaries, or that the smallest square to fit around that squiggly thing. So we'll do firebound box equals box firebound sin total bounds. So now we have our geometries that we can use for clipping. Let's clip our data, and then we'll plot some of it too. So let's clip our modus data to the, excuse me. Ooh. Didn't like talking about modus or something. Okay. Modus clip geometry equals modus spans pre dot rio dot clip bound sin dot geometry all touched equals true from disk equals true. Awesome. Now let's clip to the bounds. So modus clip equals modus bands pre dot rio dot clip firebound box, and below we're going to compare the difference between these two to see what we're actually doing. All touched equals true from disk equals true. Okay, so let's get our clipping. Okay, all touched. Spelled touched wrong. Okay, so we have our modus data clipped twice. So in two different ways. Now let's plot those two different clipping methods and see the difference. So we'll set the extent of our plot and then actually create a plot. Extent, plotting, extent, modus clip 0 dot values, modus clip dot rio dot transform. Okay, and now we'll do figure AX1, AX2. So it's a figure with two axes using the PyPlot subplots, 1 by 2, and we want a fig size of 12 by 15. Awesome. Apologies if you hear my stomach rumbling. I think I'm a little hungry. Okay. So let's plot the geometry clip. So we'll do ep.plot RGB modus clip values. RGB equals 0, 3, 2. AX equals AX1. Extent, extent equals extent. And then title equals modus clipped to geometry. Or no, clipped to bounds, excuse me. Okay. And then plot that fire boundary or bound sin dot boundary dot plot AX equals AX1. Now let's plot the modus data clipped to the plotting or to the boundary clip, the square that we created, or no, just the no, okay, I'm getting all mixed up. So the first one we're doing is to the bounds, which is the square, and the second one that we're plotting is clipped to the geometry, so it's following more closely the outline of the fire boundary, and so you might run into issues with data completeness. So let's plot that. ep.plot RGB modus clip geometry dot values RGB equals 0, 3, 2, AX equals AX2, extent equals extent, title equals modus, clipped to geometry. And then we want to do another fire bound sin dot boundary dot plot AX equals AX2. And then finally a PLT show. And now we can compare what our data looks like when we clip using bounds of the fire extent versus directly using kind of the fire extent geometry. And so for the purposes of visualizing information to an end consumer or stakeholder, in my opinion, the clipping to the bounds just looks better when you don't have this no data, this missing no data. Granted, you're including some information you might not need for your analyses, but for the purposes of presentation, this might be a little nicer. Likewise, if you're doing anything with like nearest neighbor calculations or smoothing or interpolation, it might be helpful to keep these values as well, because when you're doing it here, you're not really able to do any kind of inference because you're just missing information. And so for the purposes of NDVI and NBR, we're interested in the surrounding areas as well as the pixels directly inside the geometry. And so for this analysis, we're going to be using the clip to bounds method and not clip to geometry. And so that's something to consider when you're doing future analyses as well. So now let's explore our cropped data. And we're going to use another tool. Instead of plot RGB, we're going to do plot bands, and we're going to plot our data. And so let's create another list. This will be of titles, red, NIR, blue to green. And so these are the modus bands that we have downloaded. Green, NIR, mid, IR, IR. So you can see there's some overlap in naming, but the actual spectral window is slightly different of data they're collecting. So now let's plot these bands for the modus clip data. EP plot bands, modus clip, 3 columns, title equals titles, which is the list that we just created. And let's set the fig size equals to 10 by 6. And then BLT show. So here you can see distribution of the cropped images that we have for surface reflectance for the pre-Cold Springs fire. And so we'll compare this with post-fire activity. So now let's plot some histograms. Similarly for this band data. So let's create a list of colors. Blue, R, red, black, blue, green, black, yellow, and then yellow again. Okay, we have the same titles from above, so I'm not gonna, I guess I can just copy paste this. And then let's plot our histograms. Again, using earth-pi plotting with a nice handy hist method. So we'll do modus clip dot values, colors equals colors, title equals titles, calls equals 2, and then PLT dot show. So nice that we're able to like loop through the whole data set and just create these histograms per band nicely. And so you can see the distribution of data across each of these bands. But like we kind of previously mentioned, the ranges of values, the shape seems reasonable, but the actual values seem very wrong. They should not be in the 0 to 3,000 or thousands range. They should be from 0 to 1. And so let's scale that data. So as you noted before, reflectance values should be between 0 and 1, with 1 being the brightest, 0 being the darkest. And our data actually came with a scale factor, which enable us to kind of transform the data into the appropriate scale range, i.e. 0 to 1, from the values that are stored. It's easier to store integers as compared to decimals. And so, and this is on computers specifically. And so I think it's easier for them to store this reflectance information as numbers in the thousands as compared to a variety of numbers from 0 to 1 using floating point precision. So let's scale our MODIS band data and see what happens. So MODIS bands pre-scaled equals MODIS clip times 0.000, oops, 1. Okay, cool. Now let's check the minimum and maximum values of our scaled data. So MODIS pre-scaled dot or 1 dot min. And so this is specifically the minimum value of the red band, 0.2496. That's nice. And then let's do max. 0.3. Okay, that's cool. That's between 0 and 1. I like that. Now let's plot it again. Let's plot our scaled data, the histograms. So I'm going to reuse the colors and titles lists, and we're just going to do EP MODIS bands pre-scaled values, colors equals colors, title equals titles, calls equals to plt.show. And now you'll note it's not nicely rendering the scale range for the other charts, but they're all between 0 and 1, as opposed to in the thousands here. So now let's save our changes, commit our changes, and proceed on with the next lesson. I believe this is lesson 4. Okay, cool. Half done. Sick. Are there any questions so far as we're about halfway through today? The chat seems pretty quiet, and I've literally heard no one unmute themselves, so I'm assuming we're all good. Not actually sure how many people are still here. Oh, there's 13 still. Sick. Okay, cool. Fighting. We're getting it. Now I'm going to create a new notebook called Get MODIS. IPYNB. We're going to learn about how to download MODIS data from the Earth Explorer website. Likely we're going to skip most of this lesson just because I'm not going to have us walk through that in class. But let's have this Get MODIS. We'll select the Python 3.10.13 kernel, and then I will toggle to the lab. So we're going to learn about different MODIS products available on Earth Explorer and their unique qualities, and then learn how to get MODIS data from Earth Explorer. So this is likely another no Python lesson. Yes. Okay, cool. So it'll just be a bit of me talking. So let your fingers rest from typing. No one needs to get carpal tunnel today. So, MODIS products, Aqua and Terra. So MODIS, unlike Landsat satellites, is not just one satellite. MODIS consists of two separate satellites with distinct missions. The appropriately named Aqua and Terra satellites both focus their data collection on their area of specialty, water and land, respectively. For land-based Earth analytics projects, such as calculating NDVI or NBR, you should generally be getting your data from the Terra satellite, as it is the one that focuses on land-based data collection. So products made with MODIS data. Where Landsat 8 collects 11 bands of data, the MODIS satellite collects 36. Due to the large number of bands, much of the MODIS data that is available for download is pre-processed heavily to make it more easily accessible. Below is a list of all the MODIS products available to download from USGS. And you can see it's a broken link, so their data is messed up, but yeah, sorry about that. So there's a lot of them apparently. And so for general Earth analytics products, such as calculating NDVI or NBR, the surface reflectance products are fairly standard products to use. You can see a complete list of available products that use MODIS data here. And I'll share that link in chat in case you're interested. And note that it's much easier to use the pre-processed data, such as surface reflectance, and not the more raw data, like raw radiance product. Surface reflectance and other products like it have already been geolocated and have had a number of atmospheric corrections applied. Raw reflectance and other level 1 products have not had any processing done, so I would generally avoid those for your use cases. So now zooming into the surface reflectance products, you may notice that once we narrow our search down to the surface reflectance products from MODIS, we still have a ton of options. A bunch of the mod 9, and then like what the heck are they even? What do these mean? And so the name of each product contains some information about what the products consist of. So for surface reflectance, the second letter of the name is either an O or a Y. O means, or 0 means it came from Terra satellite, and Y means that it came from the Aqua satellite. So if you want land-based data, you would be looking to choose a product that begins with MO. So here you'll see there's MO, MY. So these are the Terra-based products. These are the Aqua-based products. By hovering over each product name, you can find out more about the product. And you can also find more data on each product on the MODIS website. MODIS products vary wildly. So MODIS makes a complete pass of the Earth daily. Some products are created daily based on individual readings for the day, whereas others are weekly averages of an area to help account for cloud cover and other interference that can occur from day to day. Some products are even yearly, such as the MODIS land cover product, which is a composite of an entire year's worth of data. So that make sure when you're downloading data or accessing it that you're aware of the actual temporal resolution that you're selecting. So a product like Mod 09GA is the highest resolution daily product that has all 7 wavelengths available in it. It's the base for many other products created for MODIS data and used frequently for Earth analytics projects. You'll notice that there's also a daily surface reflectance product with a higher resolution called Mod 09GQ. However, this product only has bands 1 and 2, as the rest of the MODIS bands are not high enough resolution to be released in this product. As we saw previously, a few of the bands are 250 meter resolution, whereas the rest are 500 or more, and so that's why. So for surface reflectance, there are also averages collected over 8 days, such as Mod 09A1. An advantage of this data over the daily data is that since it's a week-long average, it allows for some layers of data, such as the surface reflectance 500 meter state flags quality control layer, to be higher resolution than the daily products. So just some things to consider when you're selecting which data to use for your analysis. And now we're gonna talk about how to download MODIS data, kind of at the high level overview. We're not actually gonna do it, but uh, just continue listening. So downloading MODIS data is fairly simple and very similar to downloading any other type of satellite data, such as Landsat data. The first step is defining your study area because you don't really want to download all the data. It just kind of takes up space on your computer unnecessarily. And it's taking up resources on the USGS computers to share the data with you and having to send it over the internet. So it's just like unnecessary to request more data than needed. And so defining a study area or area of interest is paramount. For MODIS, be sure to use a square, rectangular, extent polygon, because if you have too many vertices in your extent polygon, you might run into errors with the website. I think they just expect a certain threshold. And if you go past that, it just freaks out. You can also define, or you can upload a zip file. You might be able to do it manually there, but I don't think so. Like selecting locations on a map. So I think the best bet is to just have a zipped up file to upload. And we learned how to do that today already, how to create that total bounds rectangular outline. You'll need to make sure to have an account so you can upload your shapefile extent to search for data. And you're going to do that using the KML shapefile upload in search criteria. That's cool because you'll just have access to whatever data they have that covers your study area. And then you'll need to define which data you want to download after kind of parsing through what's available. For this course, if you were downloading data, we'd ask you to get the MOD 09GA because that's the surface reflectance data product that we're using today. And this is a screenshot of that kind of experience. And then finally, or almost finally, you're gonna define any additional selection criteria. You cannot limit results by percent cloud cover, unfortunately, like with Landsat, but you can limit results to just be images taken during the day and not at night because you don't necessarily want a bunch of dark data. And then you can view your results and submit your order and download it. So these are the high-level steps of how to actually download data with MODIS. I encourage you to get some practical experience with it. You might not ever need it in your actual day-to-day work, but it's good workflow to at least have some high-level familiarity with in case you're ever required to access that data. Since this was another lesson that didn't really require Python, let's just do a simple print statement. Downloading MODIS data is easy. Save our change and commit to our repository. This is lesson 5 out of 8 for today. So we're getting there. For the remaining 3 lessons of today, we're actually going to be calculating vegetation indices and not just talking about like satellite sensor statistics and stuff like that. So hopefully the last 3 are a little more engaging and interesting for you. I'm going to now create a new notebook called Veg Indices. So touch veg indices.ipynb. Let's select the Python 3.10.13 kernel. And then I'm going to quickly toggle to the instructions. So in this chapter, we're going to learn how to calculate vegetation indices like NDVI and NBR from multispectral remote sensing data. And so before we do that, we're going to describe what a vegetation index is and how it's used with spectral remote sensing data. And we're going to zoom in on NDVI and NBR and describe how they're used to quantify vegetation health and fire severity, respectively. And we're going to do this all with Python and on the Cold Springs Fire dataset. So we already have the data. We don't have to download that. So we're going to just jump into the overview. So a vegetation index is a single value that quantifies vegetation health or structure. The math, scary word, with the vegetation index is derived from physics of light reflection and absorption across bands. But for instance, it is known that healthy vegetation reflects light strongly in the near infrared bands and less strongly in the visible portion of the spectrum. So thus, if you create a ratio between light reflected in the near infrared and light reflected in the visible spectrum, it will represent areas that potentially have healthy vegetation. So taking that concept in practice, let's talk about NDVI. So normalized difference vegetation index is a quantitative index of greenness ranging from 0 to 1, where 0 represents minimal or no greenness and 1 represents maximum greenness. NDVI is often used for a quantitative proxy measure of vegetation health, cover, and phenology, or the life cycle stage, over large areas. And so here we see a graphical depiction of kind of NDVI calculation and how it plays out on the greenness of trees. And so NDVI is calculated from the visible and near infrared light reflected by vegetation. And so on the left, we have a depiction of healthy vegetation that absorbs most of the visible light that hits it, but reflects a large portion of near infrared light. Unhealthy or sparse vegetation, in contrast, reflects more of the visible light and less near infrared light. And this is from NASA. And so you can see in this calculation, the NDVI value for this healthy vegetation is 0.72 in contrast to 0.14 in the unhealthy or sparse vegetation example. So now, how to derive NDVI from multispectral imagery. This is the formula that's used. It is NIR minus red divided by NIR plus red. And don't forget the order of operations. So parentheses, exponents, multiplication, division, addition, subtraction, PEMDAS, however you pronounce it. So it's this this subtraction operation and this addition operation, and then you take you do a division operation on the results of those two. So here's an example of NAIP derived NDVI data for the Cold Springs, Colorado fire. Wait, is this really another no code lesson? Damn. Okay, sorry. All right, so normalized burn ratio. Pivoting away from vegetation health to maybe more like vegetation death or the absence or eradication of vegetation. NBR is used to identify burned areas. Its formula is similar to the normalized difference vegetation index, except that it uses near infrared and shortwave infrared instead of the red. So it's a very similar type of normalized difference. So the near infrared and shortwave infrared parts of the EM spectrum are a powerful combination of bands to use for this index, given vegetation reflects strongly in the NIR region and weakly in the SWIR region. Alternatively, it has been shown that a fire scar, which contains scarred woody vegetation and earth, will reflect more strongly in the shortwave infrared part and beyond. And so here in this figure, we show the entire electromagnetic spectrum of light, the different regions. Here's the visible region, here's the near infrared region, and here's the shortwave infrared region. And then we compare two types of landscapes, the first being healthy vegetation, where you notice bumps in NIR and a kind of a lack of values in the shortwave infrared, in contrast to a burned area with woody, scarred vegetation and earth. We see a marked depression in visible and near-infrared radiation in contrast to a ton of shortwave infrared reflectance. So NBR bands. This index was originally developed for use with Landsat TM, so thematic mapper, and enhanced thematic mapper plus bands 4 and 7, but it will work with any multispectral band that has a near-infrared band between 760 and 900 and a shortwave infrared band between 2080 and 2350 nanometers. So this index can be used with Landsat 8, MODIS, and other multi or hyperspectral sensors, which is pretty cool. So the table below here shows the band distribution of Landsat 8, which is a newer sensor in the Landsat family of the Landsat platform. And so the bands are different from Landsat 7. And so question for you is, which bands do we use to calculate NDR? Similarly, this table shows the bands for MODIS. What would we use for MODIS? I'm not actually going to ask you that as a question or test. It's more just like a thought-provoking, like, oh, what would you use? So here's an example of a Landsat-derived plot of pre and post-fire normalized burn ratios. So this is after the fire, actually, because the fire happened in early July. So here we notice the scarring, where the place that has a bunch of burns that occurred has a fairly low NBR value of -1 or approaching that, whereas the healthier areas that didn't burn, the green indicates that it's unburned. But as we mentioned previously, oftentimes you don't want to just take a static snapshot of normalized burn ratio, but you want to create a difference raster to compare the values before and after a fire. And so in many places, it's helpful to have a difference NBR instead of just the raw NBR value. So here we have some kind of general ranges of values for the DNBR range and severity of burn, just as some kind of, we'll probably use these to create a classified image and remaining part of class today. And then how severe is severe? Keep in mind that this classification table above is a quantitative interpretation of what the results actually mean, but it might vary on the ground. And so the best way to verify your classification approach is to actually check the on-the-ground conditions. That's it for this one. I'm not going to really jump into false positives, but it's important to remember that this index is sensitive to water. So sometimes pixels classified as high severity burn might just be water. So let's actually toggle back to code. Oops. And for this one, we'll just do another print statement. Vegetation indices seem powerful. Let's save that, commit that to our repository, and then continue on with the final 2 lessons of the semester, actually, which is kind of crazy to say. Okay. Whew. So now let's create a notebook called NDVI. Let's open it and select the Python 3.10.13 kernel. And let's toggle to that lesson. So we're going to calculate NDVI using NAIP data. And then we're going to export or write that NDVI data to a TIFF file, and all with Python. So sometimes you can download already calculated NDVI data products from a data provider. However, in this case, we don't have a pre-calculated NDVI product from NAIP. And so we're going to have to calculate NDVI using the NAIP imagery / reflectance data that we've downloaded from Earth Explorer. We're not actually going to do that. And so, yeah, we have data. We don't have to download it from Earth Explorer. We have some provided data already, so don't worry. And as a reminder, here is the NDVI formula. And we're going to perform this calculation using NumPy. You don't necessarily have to use NumPy. You can use EarthPy or Rio, but we'll get some practice using a few different methods, I think, for the remainder of today's class. So now let me toggle back to GitHub and let's import the required libraries and continue with the hacking. Import OS, import matplotlib.pyplot as PLT, import NumPy as MP, import Rio X-ray as RXR, import GeoPandas as GPD, import EarthPy as ET, import EarthPy Spatial as ES, import EarthPy.plot as EP. We have the data already, so I'm not going to download it again, but I will set the working directory. OS Chadir, OS path join, ET, IO home, Earth, analytics, data. So now let's open up the NAIP data that we're going to use to calculate NDVI. We're going to use data from 2015 for this example that we downloaded from the Earth Explorer. So let's get to it. NAIP data path equals OS path join Gold Springs Fire NAIP, a nasty string I don't feel like copying right now, or typing, so I'm just copying that. Crop, and then another nasty string I don't feel like typing. Then we're going to open that up with Rio X-ray equals RXR open raster IO NAIP data path. And then let's view the shape of our data. Oops, NAIP data shape. So it's 4 bands of data, about 2,300 by almost 4,400 pixels. So let's calculate NDVI using regular NumPy array math. Do that like this. NAIP NDVI equals ES normalized diff NAIP data band 3, or the third or fourth band, NAIP data 0, first band. So we calculated NDVI. Awesome. Let's plot our NDVI. So it's actually like super quick and simple to do this, which is kind of nice. EP.plotbands, NAIP, NDVI. CMAP equals pink, yellow, green. Scale equals false. Vmin equals -1. Vmax equals 1. Title equals NAIP derived NDVI. ELT show. And we have a beautiful NDVI image of our data site. Let's view a histogram of our NDVI values. ep.hist, NAIP, NDVI dot values, big size equals 12 by 6, title equals NDVI histogram. Delete this and delete a 1. And let's get a plt.show. And here you'll see, I misspelled that, NDVI. And we have our histogram of our NDVI data from 2015. Now let's actually export our NumPy array to a raster, like a georeferenced raster. And so we'll do that like this. NAIP NDVI outpath equals OS path join cold springs fire outputs NAIP NDVI dot tiff. And now let's write our data to the raster object. NAIP dot or NAIP underscore NDVI dot Rio dot to raster, and then NAIP NDVI outpath. And now we have a new data there. So let's do ls gold springs fire outputs. And you'll notice that we have an NAIP NDVI file now, which is super cool. And this is a georeferenced TIFF file. Let's save our changes to this notebook, commit it to the repository, and then proceed to the final in-class lesson of the semester. Okay. Now I'm going to create a file called, so where do downloads from the code spaces go? From Talissa. They live on this computer that is created by GitHub. You know, it's like a cloud computer. We could save it to this repo probably here. We're just doing some fancy things with the working directory to access the data, you know, like the OS Chadir stuff. That's why it's saving directly into the Cold Springs data. But you can kind of, so hold on, ls, no, I don't want to touch ls. Oops. We're running ahead of schedule, so we can. Okay, so it's like somewhere in, it might be in temp ls. Okay, no. It's somewhere. I mean, so it's like the, let me open the NDVI one. What was this path that I was using? Cold Springs Fire? You gotta find that. No such thing. Cold Springs Fire. Okay, so it's not going into data. It's, where did we save it? Here. So OS ETIO home. So what is this ETIO home location? Earth Pi. Let's try to do like an LS one. Where is ETIO home? ETIO. Okay, hold on. Import Earth Pi as ET. Home slash code space. Okay. So let's do LS code space Earth analytics data cold springs fire outputs. Okay, NDVI NAP and I.tiff. Okay, so that's there. I'm gonna move this now to what is here? Okay, I'm gonna try to move it here. So the command we want to use is mv command. So it lets you move files from one location to another. So the source file to the destination file. So I'm going to do mv, and then we're going to try to move that home. I forgot. What is that path? Okay. Home, code space, Earth, analytics, data, Cold Springs Fire, outputs, NAIP. Okay, and we want to move that to here. And we're just going to call it NAIP ndvi.tiff. Let's see if that works. I expect if it works like I hope it does, we'll have a new file show up here. And we did. So that's how you can move it to here. And it can't really open this file because it's large and it doesn't really know what to do with it. But you have that data. So very cool. I'll copy paste this into here. And I'm going to save that. And then I'll commit these changes so that you have them in my demo repo. Locate output file. So it's just taking a second to upload that data to the repository. But yeah, that's where the downloads go for data. So I'm going to close this. Still thinking, which is fine. It's probably because it's not used to uploading like image data. But I'm going to now create the final notebook for today called NBR. And we'll get started. You can see the computer's having a tough time. It's probably a little too much thinking. But in the meantime, I'm going to pivot to the instructions so you don't have to struggle and watch that. So we'll notice now that actually, let me quickly show you that it in fact saved the image file to the repository. It's not going to render because GitHub doesn't know how to display TIFF files. You can see we have a TIFF, which is cool. So let's do NBR. Let's select the Python 3.10.13 kernel, and then I'll return to the instructions. And so really the main point of this lab, learn how to calculate the DNBR image, the difference normalized burn ratio image. And so as we previously discussed, you can use DNBR to map the extent and severity of a fire. And in this lesson specifically, we're going to learn how to create an NBR using Landsat data. And then we're going to calculate the DNBR by opening pre-fire data, post-fire data, calculating NBR with both, and then calculating a difference NBR by subtracting post-fire from pre-fire. Finally, we'll classify the DNBR raster using the classification table that we looked at previously for the severity classifications. So we're jumping right into code. So I'm going to toggle over to GitHub code spaces, and we're going to get into it. Import OS from glob, import glob. How are we doing? How many people do we have left? We got 10 participants left. Okay. The final view. Matplotlib, pyplot, SPLT. Didn't spell this correctly. Matplotlib. From matplotlib.colors, import listed color map. From matplotlib, import patches as m patches. From matplotlib, import colors. Import Seaborn as SNS. Import NumPy as NP. Import NumPy dot masked or dot MA as MA. It's the masked array functionality. From Shapely geometry, import mapping box. From raster.io, plot, import plotting extent. Import xarray as XR. Import Rio xarray as RXR. Import GeoPandas as GPD. Import EarthPy ET. EarthPy spatial as ES. Import EarthPy plot as EP. And then let's set some prettier plotting with Seaborn. Set style, white. SNS set, font scale, 1.5. And so now let's download the Landsat data. We already have the Cold Springs fire data. We do not have the Landsat data. So let's do that. So do data 2 equals ET data, get data, CS test Landsat. And then I'll set the working directory to ET.io home Earth Analytics data. And this will run whenever that other cell runs or completes downloading. Hopefully it doesn't give me grief like that last time. Okay, no, it downloaded. We're good to go. Let's recreate that combined TIFs function that we used previously. If we were doing a best practice, we'd have a separate Python file with this function, so we could just import it, like import like from utils, import combine TIFs, which actually, let's try that. It's the last day. Let's have some fun. Touch utils.py. Let's put the defined or the combined TIFs in here. define combine TIFs, TIF list out XR equals for I TIF path in enumerates TIF list out XR dot append RXR open raster IO TIF path masked equals true dot squeeze out XR I band equals I plus 1. Turn XR cat out XR on the band dimension. Okay. So we have this file now. Let's save it. I should be able to, from utils, import, combine TIFs. No module utils found, which is fine. It's probably because I didn't export it correctly. Hold on. Save function into py file. I think I'm just doing something wrong. No, this is not what I'm looking for. I'm on pi. So no module named utils. That's fine. It's because I think it's because I created it after I created this one. Let me try to restart this. See if that helps. Restart. So we did that. Should have the data. Let's try to do from utils, import. And if this doesn't work, I'll just move on. Combine TIFs. Yeah, no module name. Cool. It's not worth it. Import utils dot combine TIFs as combine TIFs. Will this work? Perfect. Okay, cool. Let's just skip that. It's not worth the trouble. I'm just doing something wrong somewhere, which is not a big deal. So I'm going to delete this utils.py, and then I'm going to just paste that code in here. So we have our combined TIFs function available locally, and I'm not going to do any funny business. Let's do all land sets, bands, path, blob, OS path, join, Cold Springs, fire, Landsat, collect, and then a bunch of nasty stuff that I am going to copy paste. Awesome. Next, let's sort those bands. And then combine the TIFs using our combine TIFs function. TIFs all Landsat bands path. And then let's create a new variable to just save the extent of the data for plotting to make that more easily. Landsat equals plotting extent. Landsat post fire 0 values. Landsat post fire Rio transform. And we can output our data array object. Now let's open our fire boundary and we can reproject it to match the Landsat data. So we'll do fire boundary path equals OS path join cold springs fire vector layers fire boundary geomac, and then this string that I do not feel like typing. So then fire boundary equals GPD read file fire boundary path. And then let's reproject it if the CRS are not the same. So fire bound UTM Z13 equals fire boundary the CRS Landsat post fire.rio.crs. And so now we have projected data ready to use. So let's calculate the NBR on the post fire data. Just remember to use different bands than the NDVI. Similar formula, but different input data. And so because this is Landsat 8, we're going to be using bands 7 and 5. And remember that counting starts at 0 in Python. And so indices 2 and 0 when we're accessing them or accessing them in Python because we just have bands 5, 6, and 7. So let's calculate our normalized difference. So we'll do Landsat post fire NBR equals Landsat post fire 0 minus Landsat post fire. So here we're manually doing the math instead of using the EP normalized difference function. So there's different ways to do this. Landsat post fire 0 plus Landsat post fire 2. Okay, so that's our NBR for post fire. Now let's plot it using PyPlot. Big X equals PLT subplots. Big size equals 12 by 6. EP plot bands. Landsat post fire NBR. CMAP equals PIYG. V min, value min is -1, value max equals 1, AX equals AX, extent equals extent Landsat, and then title equals Landsat derived NBR. And then let's overlay the fire boundary on top of that raster imagery. Plot AX equals AX. Color equals none. So it's a hollow transparent fill. Edge color equals black. And line width equals 2. plt.show. And now we'll see I have a typo. It should be vmin, not vmap, or cmap. And so here we have our NBR data with our overlaid fire bounds that match up quite nicely. Next, let's calculate NBR for the pre-fire data. Cool. Oh, so they don't actually have the post-fire data for us here. It's super annoying. Yeah, let's see what data they actually have. So I'm not going to go to Earth Explorer with you all today. Just being real. Let's try to figure out what these days mean. So that's LLC 2016-07-07. Okay, cool. So I'm going to use this first folder because I think this is pre-fire. And let's see what happens. Because I believe we're using the other data set for post-fire. Or no, 7-11. Oh no, that's the fire boundary. Okay. We're doing sleuthing here. So this is the 2016-07-23. Okay. 2016-07-23. Okay, cool. So let's use this first one then. So we're going to do some very similar steps. I'm going to copy paste these and we're going to tweak them a little bit as we go. So we first got that one. Then let's do this. And we're going to have to change a lot of these values and make it pre instead of post. And then finally, we'll do a plot. So let me change these values to this one here and see what happens. And so actually we have to, we should be good. Okay. And let's call that pre-fire. I don't need to do that extent thing again. And then Landsat pre-fire NBR. And then let's change these values here. So we should be good. Now let's try that and see if we get any errors. No, okay. Now let's try to plot our pre-fire NVR. Let's see what that looks like. Got an error, which is fine. Plot bands expects the number of plot titles to equal the number of array rear lasters. Okay, so I might have a typo here somewhere. Is this not a single layer? No, it is. It's a single data array. Okay. Interesting. Let's try this instead. Oh, I might have just put in the wrong data. Yeah, that's why. So you can see here, this is the pre-fire NBR, and you'll note that there isn't associated low values of NBR here because it's before the fire. So if I quickly scroll up, this is after fire, and let me rename. Let me do the title. Landsat post fire Landsat derived NBR, and this one is pre-fire Landsat derived NBR. So now let's calculate the difference between the two rasters. And we'll do that like this. dnbr Landsat equals nbr Landsat pre-fire minus Landsat post-fire nbr. And then we can output that, and you'll see we have a new data array. Now let's plot that data array. But first, let's create some categories. And so we're going to classify our data so that it's grouped by high severity, moderate severity, low severity, unburned, and enhanced regrowth. And so those are reflective of specific NBR regions or DNBR ranges. And so let's codify that into some Python real quick. So we'll create some classification bins. So DNBR class bins equals negative numpy or negative infinity to -1 or to -0.1, -0.1 to 0.1, 0.1 to 0.27, 0.27 to 0.66, and then 0.66 to positive infinity. And so now let's create these classes by applying the np digitize function to our data. So we'll do dnvr Landsat class equals xarray.apply ufunc np digitize, and then you want to do dnbr Landsat, and then dnbr class bins. And then we can output that dnbr Landsat class. Because I have a typo. Also, a data array object, single band. Now let's make a nice looking plot. So we have category names. Let's make a list of category names. dnbr cat names equals enhanced regrowth, unburned, spelling man, low severity, moderate severity, high severity. And then let's do NBR colors, another list. And we'll do green, yellow green, peach buff, it's a good color name, coral, and maroon. And then we'll create a color map for our NBR using listed color map on NBR colors. So cool. This is going to be for our legend, essentially, these category labels and the colors. And so now let's actually plot our data using our custom legend. So we'll do, but first let me get some coffee, sponsored by Trader Joe's. Okay, TNBR Landsat class plot equals MA dot masked array DNBR Landsat class values DNBR Landsat class dot is null. Cool. Now we can create the plot. Fig X equals plt dot subplots. Fig size equals 10 by 8. Fire. Bound. UTMZ13 dot plot AX equals AX, color equals none, edge color equals black, line width equals 2, classes equals NP unique, DNBR Landsat class plot. Classes equals classes dot to list, and just the first 5 entries. So now we'll invoke EP plot bands, EP draw legend, and then plt.show. So we'll do EP.plot bands, DNBR, Landsat class, plot, CMAP equals our custom NBR CMAP. Vmin is -1, or no, there's 1, excuse me. Vmax equals 5, because these are categorical labels. Title is Landsat DNBR Cold Springs Fire Sites. And then let's turn off the color bar, scale bar, set the extent to Landsat extent, and set the axis to AX. And now let's draw a custom legend using the draw legend method. The image axis is ax.get images. We just have one image, and then classes equals classes, titles equals DNBR class or cat names. Is that even a variable we have? Oh, it is. Okay. I already forgot. Goldfish memory. plt.show. And you can see we made a pretty involved, fancy looking map classifying our landscape according to this kind of normalized or DNVR classification scheme. And you can see where the highest severity burns were and the places that didn't really experience any damage, or if anything, experienced some regrowth following the fire here. So now let's create a color bar legend. It's a bonus that I'm going to skip. So as the final section of this lab and of this class, let's export our DNBR raster to a geotiff. So we'll do DNBR path equals OS dot path join I already forgot, and then I guess we'll just do current. Let's see if this works. How did I do it with this one here? I already forgot. Okay, yeah, no, I just did dot slash. Okay, cool. And then say DNBR landsat.tiff. So let's export our data as integer 8, just because it's nice and compact for storing. Landsat.class.rio to raster, DNBR path. D type is int 8. So do we have a new TIFF? No, we don't. That's fine. Let's because we're outputting it into that outputs folder, which is fine. So let's just do, I'm not going to try to be tricky here. I can always move it. Let me do cold spring fire outputs. And then we can move if we really want to. MV cold springs fire outputs DNVR Landsat TIFF land DNVR Landsat TIFF. I don't know if it's actually working or not. I don't think it is. Okay. Oh, that's why. Okay. I didn't actually reference the full path. It's just me being silly. Okay. Home data. Let's try this. Cannot access home Earth. Analytics data, cold spring fire. Okay. Interesting. No such file. Let's see what's in here. LS. Nothing. Okay, so outputs is empty. Weird. Okay. OS path. Cold Springs Fire output. DNBR Landsat path. DNBR Landsat class. Rio to raster. DNBR path. Okay. And then this is still going to be empty, probably. No, it exists now. Okay. Cool. Now let's try to move that here. Did it move? I don't see that it moved. Okay, let's try slash home slash code space. Interesting. OS home code space. Interesting. Okay. So we have this DNBR Landsat TIFF here. Oh, this is because we're using the Python. We set the working directory via Python, and I think that's why it's a little confused. But we have our file. The DNVR TIFF was created somewhere. It's just not in the most conveniently located place currently, but it does exist. So let's try to move that here. Cold Springs Fire. Data. What's in here? No. Earth Analytics. Code space. Here. Oops, that's not spelled right. All right. We're just kind of getting in the weeds of something not super important, but just wanted to say that it's been a lot of fun this semester, and we'll get sappy next week too. But that's all I really have for today, actually. So let me save these changes, commit into the repo, and then we can kind of close out together. Are there any questions regarding today's lessons? What's expected for the remaining part of the semester next week? Anything? Or are we all kind of good on what's up? Oh yeah, let's actually go to the final right now. The final opened at 10, so about an hour and 45 minutes ago. And so I'll share the link to the lab from today to give you so you can follow it. Let me open the final. So it's kind of I think it'll make you guys smile and not too much stress, but really just um, reinforcing a little bit of what we learned this semester, but also having you think about the future more than anything. And so it's really kind of some short answer questions that I have for you all that I want you to answer. So with some optional feedback that I'd love, but through the use of the GitHub Codespaces platform. And so I'll share a link to the final here, but it's already live on our course website and open in Canvas. So you can get started if you want, turn it in if you want. I won't grade until after the submission deadline, but yeah, it's open and live. So if there's any questions about it, don't hesitate to reach out, but it should be straightforward, I think.
Thank you. We really appreciate you.
Cool. Thank you. Appreciate that. But yeah, that's all I have.
Thanks a lot, Alex.
Thank you guys. Yeah, but I'll see you next week.
Have a good one.
Thanks. You too.
Thank you.
See ya. Thanks.
Hey, Professor.
Yeah, what's up?
So just to make sure, you did say you would open up that final starting today.
Yeah, it's open already. Yeah.
Okay,
I
sounds
think
good.
since 10 it's been open, but yeah, you can get started and finish it up if you want.
Okay, and I'll also probably shoot you an email. I'll be participating in the Latinx graduation on the 18th.
Okay, cool. Yeah, just send an email. Ideally today or tomorrow, just so I know. Yeah.
Okay, sounds good. Thank you. Have a good one.
Thanks, you too.
Thanks, Alex. Alex, can I ask you a quick question before we go? It's
Yeah.
about Lab 5 and on the challenge 1 for like the 10th lesson. So
Oh,
I'm just
yeah. Okay.
yeah, so I'm just looking at it and I've been trying to work on it for a bit and I just wanted to ask, so basically what it wants you to do is show like 7 bands and it wants pre-fire. So kind of just when you're doing that, and do you just basically put Landsat pre-fire path and then like get the bands you want? Is that kind of how you get the past information? I'm just like a little confused on that.
Oh, so okay. So you're trying to figure out which data to use.
Yeah, and this may be the dumbest question, but I'm just not sure because it just wants you to use pre-data. It's trying to get you to show.
This is actually the data we use today. And so it's
That's
kind
what I
of
thought.
yeah.
So when you
You
were
can
kind of
basically use today's stuff as a yeah.
okay, sounds good. Thank you. That makes
Yeah.
it a lot
Cool.
easier. I was thinking that,
Perfect.
but I just wanted to double check.
No, yeah, you're totally spot on. Yeah.
Okay, great. Thanks.
Yeah.
And see you next class. Thank you.
Cool. Awesome. Yeah. And then there were 2.
Are you still recording, Alex?
I'll stop. So give me a second. Let me stop the recording.